Hello all, welcome to this course on computer organization. The topic we'll be discussing today is multi-cycle control unit. As in case of a single cycle processor, the control unit computes the control signal based on opcode and funct fields of the instruction, bits 26 to 31 and bits 0 to 5. Figure shows an entire multi-cycle MIPS processor with the control unit attached to the data path. Data path is shown in black and the control unit is shown in blue. Here too, the control unit is partitioned into a main controller and an ALU decoder. ALU decoder is unchanged and follows the truth table as in case of the single cycle MIPS processor. Now, however, the main controller is a finite state machine that applies the proper control signals on the proper cycles or steps. Sequence of control signals depend on the instruction being executed. The main controller produces multiplexer select and register enable signals for the data path. The select signals are mem2reg, regDST, IORD, PCSRC, ALUSRC-B and ALUSRC-A. The enable signals are IR-write, mem-write, PC-write, branch and reg-write. For readability, only the relevant control signals are listed here. Select signals are listed only when their value matters. Otherwise, they are don't cares, denoted by an X. Enable signals are listed only when they are asserted, else their value will be 0. Now, let us develop the finite state machine state transition diagram for the main controller. So, the first step for any instruction will be its fetching from the memory at the address held in the program counter. The finite state machine enters the state on reset. To read the memory, IOD signal value will be 0, so that the address is taken from the program counter. IR write signal will be asserted to write the instruction into the instruction register IR. Meanwhile, the PC should be incremented by 4 to point to the next instruction. Because the ALU is not being used for anything else, the processor can use it to compute PC plus 4. At the same time, it fetches the instruction. ALUSRC-A is 0, so the source A comes from the program counter. ALUSRC-B is 0, 1, so the source B comes from constant 4. And ALU OP value will be 0, 0, so that the ALU decoder will produce the ALU control signal with value 0, 1, 0, which makes the ALU add. To update the program counter with this new value, PCSRC will be 0, as in here, and PC write is asserted. The data flow given here consists of the instruction fetch, which is shown using a dashed blue line, and the program counter increment, that is given using a dashed gray line. The next step is to read the register file and decode the instruction. The register file always reads the two sources specified in the RS and RT fields of the instruction. Meanwhile, the immediate value will be sign extended. Decoding involves examining the opcode of the instruction to determine what to do next. No control signals are necessary to decode the instruction, but the finite state machine must wait for one cycle to read and decode to complete. The new state is highlighted in blue. Now, the finite state machine proceeds to one of the several possibilities depending on the opcode. If the instruction is a load or store, the multi-cycle processor computes the address by adding the base address to the sign extended immediate. This requires the ALU SRC A to be 1 to select the register A and ALU SRC B to be 10 to select sign immediate. ALU OP will be 00, so the ALU adds. The effective address is stored in the ALU out register for use on the next step. If the instruction is a load, the multi-cycle processor must next read the data from memory and write it to the register file. To read from memory, the IOD signal will be 1 to select the memory address that was just computed and saved in ALU out. This address in memory is read and it is saved in the data register during step S3. On the next step S4, data is written to the register file. Now the mem2reg value is 1 to select the data and regdst value is 0 to pull the destination register from the RT field of the instruction. Also, regwrite is asserted to perform the write, completing the load instruction. Finally, the finite state machine returns to the initial state so as to fetch the next instruction. For this and the subsequent steps, we will not be including the data flow. From state S2, if the instruction is a store, data read from the second port of the register file is simply written to the memory. That is this value. In state S5, IOD value will be 1 to select the address that was computed in S2 and that was saved in ALU out. And memwrite will be asserted to write the memory. Again, the finite state machine returns to S0 to fetch the next instruction. That's all for now. The remaining part of the designing of finite state machine will be included in the next video. Thank you. Thank you for listening.